Okay, well, we've got a mix of Zoom and in person right now. Let's see how things evolve. But it is 5 o'clock, and I would like to be mindful of the time. And thanks for coming down. Wasn't it nice to just park right up front today? Didn't have to fight traffic and all that stuff. That's very rare around here these days. Anyway, I survived my little trip to San Diego. A little tired still from that, but I did make it back. And so, yeah, I'm going to do a couple hours of some practice problems right now. And then I'll take a little dinner break and then I'll come back and have my hours throughout the night tonight. And then kind of almost the same thing again tomorrow, except I'm going to do the review 1 hour later. I think tomorrow's review is going to be very similar to this one. I was reviewing which problems I was going to go over, and more than likely, this is already a really good coverage. So unless I don't finish these, the stuff I'm going to do in tomorrow's review will probably be very close, if not the same as what I'm doing here. So I'll try to let you know a better idea about that after we see how the review goes. But there's a chance that you might decide, yeah, you don't need to see it again tomorrow because it's going to be so much like today. However, you're welcome to come again tomorrow because sometimes people like to just soak it up a couple of times. Maybe the first time you're trying to figure it out and write it down for yourself, and then sometimes hearing it again when you just can relax and just listen can also be helpful. But it just depends on your schedule and whether you have the time and want to do that. I definitely think that a big priority for everyone should be to do the sample midterm. So this is now, we're kind of in the 48-hour zone before the test. So I would recommend that within the next 24 hours that you try to do that sample test. Sit yourself down without your notes on your own. See if you can give yourself about 75 minutes to just try to do it. And I would recommend doing it in the next 24 hours so that if you try this test and you realize, oh my goodness, there's some things I need to study, that you've left yourself a cushion of time that you would be able to then go back and work on those things. So that's what I do. I do have the solutions to the sample test there. The other thing you can do is if you take the sample test and you realize that you're not as comfortable as you would like to be, you can look at the practice problems that are in the review packet itself as like an additional source of problems. All of that is in that same folder for the midterm, the resources folder for the midterm. So you could do that. And then you can also just come hang out at my office and say, oh, I'm not feeling very good about whatever, Diophantine equations, right? So, okay, so maybe I can throw a practice example at you and have you try to work it out fresh. Okay, so anyway, as you're working on stuff, pay attention to your strengths and to your weaknesses and where you think that you need more time in terms of your studying, and then let me know if I can be of any help. Okay, I haven't graded your homeworks yet. I'm sorry. I usually do them right away, but I was so tired last night and I've been a little busy today. I'm hoping to do that tonight when I have a little bit of a slow time this evening. So that last homework should get graded before you wake up tomorrow morning. Also, I did publish the solutions to it, so you certainly can take a look at that. Hello. So great. Wow, this is the more the merrier here. I love seeing people coming down for this. Does anybody want to, well, okay, so one other thing before I get launching into the actual math for the review. Don't forget that there will be 4 of the 5 theorems. I listed those. Those are big theorems, right? The Chinese remainder theorem's on the list. Fermat's little theorem is on the list. The fundamental theorem of arithmetic is on the list, and there's a couple of others. I'm going to pick 4 out of those 5 and throw them onto the exam, and you're going to write up your proofs of 2 of those. You can use my proof. You can use the book's proof. You can really use any correct proof. I would recommend that you use either mine or the book's because if you go off onto some third-party resource that uses different notation and writes things up kind of from a different lens, it might be a little bit less clear to you, like what I'm expecting. So, but if you go with the notes, it's going to be perfect. If you go with the book, it should be perfect as well. And so be practicing those a little bit. Now that we're in the 48-hour zone before the test, this is crunch time to be doing that as well. So that'll be automatically on the exam. You'll see it there for sure on Tuesday, along with obviously the rest of the questions. So you need to be preparing for those proofs. And then, like I said, the sample midterm would be a great thing to study. Okay, I haven't written the test yet, so I don't know if there's going to be a take-home portion. There will be no other homework due next week, so you won't have anything else to worry about for this class unless I make some kind of a take-home. Like what I've done in the past sometimes is I'll say something like, well, everybody's running out of time, so maybe we should let everybody take something home of their choice. So I might do that. I have to see how long the test is when I write it as to whether I'm going to do that or not. But if I did that, it wouldn't be something that would be a huge time suck for you this week. It would be something you could do pretty quickly, and I'd probably give you just a day or two to turn it in. So that would be the only thing that would potentially come up that's not already on our radar. But there won't be any other homework due at the end of next week. We'll have kind of a week off from homework. Okay, so now I think I've said all the logistics I need to. Does anybody want to ask me any questions, just overview, broad scale tone before I actually start doing some math problems? Okay. Hi, Brian. I just talked over the whole overview of the exam. I am recording this, so you might want to watch the first 5 minutes of this video recording once I get it posted a little bit later on. So what I am going to do, I actually have about 10 problems here, and I would like to go through them. The purpose of this is not to solve them as fast as we can, as superficial as we can, but to really go into them, right? I want to try to hit the high points of the material that we're supposed to know. And I have no agenda. Like if I don't finish all 10 of these in 2 hours, that's fine, because I'll just spill them over to tomorrow. Right? What I'd rather do is have you asking me questions. I'll probably try to ask you guys questions too, just to kind of get you thinking a little bit about it. But these would be problems that I think involve the same skills I'm going to be asking you to use on Tuesday. So I thought they'd be good. It's a mix of computational problems as well as theoretical problems, which is exactly how your midterm is going to be. Also, remember, guys, on the test, there will be no calculators of any kind. I want the playing field to be completely level. So you should expect that the kinds of numbers that I'm going to ask you to work with will not be enormously difficult because you're not going to have a calculator. But they will also not be like super small basic numbers either, because I don't want people just guessing the answer to something by inspection, right? I want to see people showing me that, oh, they do know how to use Fermat's little theorem or the Chinese remainder theorem, and they didn't just like guess a value of X that was, happened to work just by inspection. So don't be surprised if the numbers are kind of medium size. There may be some that are like that on the computational problems. So I've got some examples here that are kind of that scope, so you kind of get an idea. All right, but anyway, so I've got 10 problems. And I'm just going to start from the top here. So these are practice problems for the review session. Just interrupt me as much as you want, guys, with questions, because like I said, I'm not in a hurry here. Okay. So number one is, and this is kind of going back towards the beginning a little bit. If M is a multiple of both A and B in the integers. Okay, so if M is a multiple of both A and B, then prove that the least common multiple, which is the LCM of A and B, divides M. So this is a fact that we've kind of used a few times, but maybe never explicitly wrote down this proof of this. So I thought it might be a nice one to do. as you can see, the assumption here is telling us that M is a common multiple of A and B. So I think everybody would probably agree that the least common multiple of A and B would be less than or equal to any other multiple of A and B. But this doesn't say less than or equal to, this says divides, right? So the real power of this statement is that M is not just larger than the least common multiple, it's actually a multiple of the least common multiple. That's really where this is at, okay? So this is kind of the idea. So let's just see if we can solve it. And I don't think too many of you have had me as a professor before, so I should just let you know that I am not an all or nothing on credit for a problem. So I do give partial credit for any partial progress. So maybe you look at this problem and at the beginning, you may not see how to solve it yet. Try not to let that throw you into anxiety and stress, right? Because what you want to do is don't worry about solving the whole problem yet. Just tell me what you know that is related to the given information. I mean, you shouldn't just go off telling me about stuff that's irrelevant to this problem. Like if you decide, oh, I think I'll just state the Chinese remainder theorem. Well, that's not really relevant to this problem, so I probably wouldn't give you anything for that. But if you wrote down what it meant for M to be a multiple of A and B, that is a starting point on what a proof might look like. So you should write that down, even if you don't see the full solution, because then I can give you some credit for it. If you don't write anything down, I can't give you any points. And I want to give as many points as possible. So in this case, the assumption here is that M is a multiple of A and also a multiple of B. So maybe we could try to turn that into some math language, right? So by assumption, M is a multiple of A. Let's just take that one. Can we write that as an equation? Yeah, so A divides M, and can I write that as an equation? If I know that one number divides another, does that turn into an equation?
A equals MK, so K.
A equals MK, does that look right?
M equals AK?
Yeah, it should be M equals AK. M is a multiple of A and of K. So M is equal to AK. And I would want you to clarify when you're introducing new notation where the new notation lives. So K in this case is an integer. So you should say that. If I just see variables if I see things from the question showing up in your solution, that's fine, right? Because it's already been set up for you. But if you introduce some new letters into your solution without explaining them, I might pick on you a little bit on that. At least you've got something written down, but it would be better to really clarify what these variables are representing. Okay? You able to see this okay in Zoom land?
Yeah, it looks good.
Awesome. Thank you. Thank you. Okay. So M is equal to A times K. And what else might we want to write down? Same kind of thing for B. So M would equal, what would we want to use? Yeah, how about BL for some L in the integers? Of course, the L and the K are not necessarily the same. So I wouldn't want to assume that. Okay, and this LCM of A and B, just for convenience, this isn't really strictly necessary, but just to make our life a little bit easier, we could just call it C. So C is going to be our notation for the least common multiple of A and B. And what we would like to show, we need to show that C divides L. That C divides M. Any thoughts on, now we're ready to get to the main step of the argument. So far we've set up the assumptions. Now we've got to think about how are we going to prove that M actually divides C. Are there any thoughts on what we could potentially do here? Yeah, please.
Divide C and divide C.
So A does divide C because C is a multiple of A. So A divides, I'm going to write this over on the scratch paper over here. A divides C and B divides C. Okay, that sounds good.
equals A times something, and then C equals B times something?
Yeah, so C would equal, let's say, A times X, and C would equal B times Y. This would be for some integers X and Y. So all of this would be true, right? And that's relating the C with the A and the B. Ultimately, we want to relate it to the M. Is there a way to put this together to get the M to show up? It needs to be M equals C times something. We have C in terms of A and C in terms of B, but of course there's no mention of the M here. Yeah?
Can you multiply by both sides? That equation, and you know what happens? Or,
So multiply through by M?
yeah, I'm just gonna.
Yeah, thinking out loud. Yeah, we could algebraically introduce M into this if we wanted to. Another way to bring the M into it would be to, because we know we need to use this assumption, right? We could bring the M into it by solving for A and B. So I'm still over on my scratch paper, by the way. So the C was equal to AM. Well, AX. C was equal to AX. And A can be written as M over K times X. So we could relate the C to the M that way. Right? Or we can do the same thing with the other equation, with the B and with the Y. Does this convince me that C divides M? In other words, does this divide, this is a question, does this divide M? Well, we don't really have a connection between the K and the X. Like, I don't know, the K was introduced over here, the X was introduced over here. They aren't really jiving with each other in a way that I could say for sure that C divides M. So it would need to be that this thing times an integer was equal to M. And we actually know what the integer would be. If I took this thing, I would have to multiply it by K over X to get M. But the problem is I don't know if K over X is an integer. If it was, that would totally work. But the K is here and the X is here and they're integers, but when I divide them, if I do K over X, it's not so clear to me. So as much as I kind of like this approach, is certainly everything here is correct, I think we're going to need a different way to prove that C divides M. And it's kind of in line with like a general strategy to proving that one number divides another. If I wanted to prove that, I don't know, if I wanted to prove that 7 divides 91, like, how could you prove that?
To show you an integer that when you multiply it by 7, you get 90.
Yeah, and like, so I have 91 and I have 7, and I want to know, how would you find the integer that works here? Yeah, just divide it, right? You would just divide it and you would get some quotient, right? And then the issue would be what the remainder is. By the way, what result am I using when I take one number and divide it by another and get a quotient and a remainder? What was this called? It's the division algorithm. You know what we can do here, guys? What we can do is we can apply the division algorithm to the M and to the C and see if the remainder is 0, right? So let's do that. Okay, let's try that. That's a different approach than what we've got over here on the scratch. But let's try this. I think this is going to work really nicely. So by the division algorithm, if we have a named result, guys, that you're using, it's good if you write it down. Give it the name. I don't care if you have the theorem numbers memorized in the book. That's not important to me. So you can, don't worry about memorizing the numbers from the book, but something like division algorithm, you should at least know what that is. So the division algorithm says that there is some quotient, which is an integer, and a value of r, which is a remainder, and the remainder is somewhere between 0 to 1 to 2, all the way up to whatever you divided by minus 1. So it's some remainder between 0 and, in this case, c minus 1. And then we're just going to say such that m is equal to q times q times c plus r. And if I could just prove that r is 0, if I could prove that r is 0, kind of like on the example there on the middle board, that would prove that c divides m. That would prove what we need to prove here. So we need to show that c divides m. So let's divide m by c and see what the quotient and the remainder is. And if the remainder is 0, we're good to go. Is everybody with that? That's a really powerful strategy for proving that one number divides another. You simply go ahead and divide them and just see if you get a remainder of 0. It's a clever idea. So now I'm going to come over here and try to take this equation. So I'll recopy it here so everybody can see it really well. M is equal to Q times C plus R. And now I would like to work with this in an effort to prove that this remainder is 0. Okay. Now remember, guys, C is the least common multiple of A and B. And notice that R is less than C, right? So the R shouldn't be a common multiple of A and C. But you know what? If we solve this for R, and then we feed in on the one hand that M is equal to AK minus Q times C. Well, the C, we did write down that A divides C, and so C can be replaced with AX. So I am actually using what we put in the scratch work on the side, right? Well, look at that. Look at that. I can pull the A out of that, and it leaves me with A minus QX. And what this proves, my friends, what this proves is that A divides R. You wouldn't need to tell me this, but I will go ahead and emphasize it here. It would be helpful. This is still an integer because K is an integer, Q is an integer, and X is an integer. So everything there is an integer in that statement. Okay? Is everybody with me? And I'm just going to say similarly, by the way, guys, you're allowed to do this also on the exam. Like if it's almost the same argument, you can just say similarly, B divides R. I'm actually going to write it out just since we have plenty of time right now. But if you were taking the test, you would certainly be welcome to say similarly, or you could at least ask me, can I say that this is similar? I've got equations for M that involve B, and I've got equations for B in terms of C as well. So I can plug all of that in. This is BL minus Q times C, which is BY. And just like before, I can pull out the B, and this time I'll have L minus QY. This, again, is an integer. And so B divides R as well. What this proves is that R is a common multiple of A and B. But also, we should point out that R is less than or equal to C. I think we're getting close. I think we're getting close, right? C was supposed to be the least common multiple of A and B. Now I have found another number, this is R, which is also a common multiple of A and B, and is actually smaller than, actually this is smaller than C. That should be strictly smaller than C. So the only way that we can bail ourselves out of what looks like a contradiction is for R to have been 0. Because when you're talking about least common multiple, you're never talking about 0. I mean, it is true that 0 is always a common multiple of everything, because you can always write any number is always 0. So 0 is always a multiple of any number, because you can just write it as 0 times whatever that number is. So it's definitely true that 0 is a common multiple, but the least common multiple of two numbers is supposed to be the smallest positive integer that divides into, that is a multiple of both of those numbers. So R had better not be a positive integer, because if it was, you would have violated the assumption that C is the least common multiple. So we conclude, I'll just say by definition of LCM, that R is equal to 0. And so if that's the case, then M is just equal to Q times C. And this implies that C divides M, and we've got the first problem good to go now. That's the first one. Questions on that? Does that look okay? By the way, you're also, not only are you allowed to use any results that we've talked about or that are from the lectures so far this semester, you're also allowed to use any of the other things that we've done. So if you want to use this fact on the test, you could just say, did it in the review session, right? It's not likely that I'm going to pick something from the review session to be used, because not everybody's coming to the review, but certainly from the lectures, right? If there was some fact, or even from the homework, right? If there was a homework problem and you're like, oh, that homework problem would be relevant here, you can just say, by a homework problem, right? Just make sure it really was from the homework, or that it really was from the lecture, because I've done all the homework and I've been to all the lectures. So I will know whether it really was part of that or not. Okay, any questions on this? Seem okay? It's pretty basic one. Just kind of, this is almost based on just the stuff from the very start of the semester, but I wanted to kind of take it from the top. Let's go on to number 2. And number 2 is also kind of in a similar way. It's a similar kind of topic. So number 2 says, if C is a common divisor, okay, so I'm switching up the role here, common divisor of A and B, prove that C divides the GCD of A and B. So it's kind of similar to the first one. You have your greatest common divisor of A and B, and then of course any other common divisor of A and B would be less than this one, right? But we're saying something stronger here. We're actually saying that any other common divisor of A and B actually must divide this one. Okay, so it's not just less than. If this said less than or equal to, you would just say that's obvious. It's just the definition. The greatest common divisor would be greater than or equal to any other common divisor. But this isn't a less than or equal to. This is just saying C divides the GCD of A and B. Okay, so this is similar to the first one. I'll go a little bit faster. Let's try and write down the proof of this. I would again recommend putting down all of the information that we know ahead of time. So I'll just say, by assumption. Another thing, guys, on the test, don't restate the question. Some people like to write out the question again. That just wastes your time. The question's already there. So just jump right into the solution. Okay, so by assumption, C divides A and C divides B. So I'm just going to say A is equal to CK and B is equal to CL for some K and L in the integers. Okay, so we can start off that way. C divides both of those things. And now I would like to prove that C divides the GCD of A and B. Maybe just like we did on the first problem, I can give another name to the GCD, just like we redefined the LCM over here. I think for this time, I'll redefine the GCD. A lot of times we use a D for that. So I'm going to let D be denoted as the GCD of A and B. Okay, so just to get some notation there. All right, and I would like to show that C actually divides T. C actually divides D, and so far we have not said anything about D. We've just introduced it as a notation. Does anybody have any thoughts or remember any results that might be helpful here?
We write D as AX plus BY.
There we go. All right, so Zoom is to the rescue. Exactly. So the reason I wanted to do this problem was to remind you about that very, very important result, which is, this was, again, very early in the semester, the greatest common divisor of two numbers can be written as an integer combination of those two numbers. So we can write, and this is by, I think it's theorem 2.3. It's actually one of the ones on your list, right? That you're learning, I hope. Okay, so by theorem 2.3, there exists an x and a y in the integers, okay, with d equal to ax plus by. So the GCD of two numbers can be written as an integer combination of those two original numbers, a and b. Excellent. Okay. And I would like to prove, let's just keep in mind where we're going, that C divides this thing. Now we already know that C divides A. Already know that C divides B. Anybody have any thoughts what I might want to do here? Plug in, right? I've got expressions already for A and B. So I can take those expressions and put them right here into this combination. I'm going to come over to this third board just to give myself just a little bit of enough room. So D is equal to CKX plus CLY, like so. Okay, and there you go. Now you just kind of turn on your algebra intuition here. You see the factor of C. We can pull it out, even if we don't for sure know what that's going to do for us. And there you go, guys. The KX plus LY, that is an integer. Again, I'd probably let you get away without reminding you of that, but it never hurts to put it there. And now you have C times some integer equaling D, and so C divides D. I love it, and it's a nice chance to use this theorem. This is a big deal. It's in your list of theorems. I think it gets underplayed in most algebra courses. People don't bring this up about the GCD of two numbers, that it's an integer combination of those numbers. Just to remind you, the X and Y here are not unique, and that if you want to obtain at least a choice of X and Y, you have to use the Euclidean algorithm forward and backwards to do that. So actually, I think in a little bit, we're going to have some examples where we actually have to do that part. But anyway, so that is another nice problem. Notice that neither of these proofs is terribly long. The only really long proofs I will have for you is going to be the ones you're learning, right? The rest of them should be pretty short. And actually, because I know some of you haven't had me as a professor before, if you look at a problem and I give you 1 inch to write the answer, okay, I'm going to space out my exam on paper for you. And that's almost a hint, right? If I only give you 1 inch to write down the answer, that probably means, okay, I'm not going to need to spend 20 minutes on this. It's not going to be some really long, complicated thing, right? The other thing to look at is how many points is the problem worth. The point values on these problems will not be based on how easy or hard the problem is. They will be based on like how much work goes into doing the problem. So if it's a problem that's worth a lot of points might be 9 or 10 points on a problem. That means, okay, yeah, this is going to be substantial. It doesn't mean it's going to be hard. It just means there might be a lot to do. Maybe there's um, a combination of Chinese remainder theorem and Fermat's little theorem, and you got to put it all together and do a whole series of steps with congruence theory. Okay, that would be like a longer problem. On the other hand, you can have a problem that maybe it's a more theoretical one that's much shorter, and that could be worth less points, but it might be more challenging. So don't equate the point values to the difficulty. That's what I'm trying to say. Equate it more to how much time, at least in my mind, I think it's going to take you to solve it. Okay, and again, go for all of the partial points you can by just writing down everything that you know as we go along. Okay, so just giving you some test strategy advice, because like it or not, I've seen really good students that don't perform their best just because they're just not putting their best forward on the test. I know they know this stuff, right? But then it just doesn't come out on the paper. And I've also seen students who I thought were really kind of a little bit shaky, but they did a really good job of telling me everything that they knew. And they ended up with a really, really respectable grade that they were happy with. So that's another thing to keep in mind. It's not just all about what you know, it's also about like communicating it. It's like getting it down on that paper during that time. Okay, let's do another one. Now let's go to something more computational. I've done a couple of sort of theoretical examples. Let's do something a little more computational. Find the 3 smallest positive integers that satisfy, and I'm going to give you this equation, 140 times x congruent to 133 modulo 301. Okay, so this is totally computational. Of course, you need to show your work, even if you just happen to plug in an x and get lucky. You have to explain or I won't give you any points for it. The other thing is that this is about the size of numbers you might expect. You're probably not going to just guess the answer in your head. I try to make the numbers big enough that that's not possible. But they're not so big that you're going to have nightmare calculations. It shouldn't be that bad. This is, of course, in the topic of linear congruences. Right, so we did a general section about solving AX congruent to B mod n. Does anybody remember the condition that has to be true for this to even have a solution?
The GCD has to divide into
The GCD of what?
140 and 01.
Right, in general, A and N, the GCD of A and N has to divide what? B, exactly. So that has to be true in order for there to even be a solution. Now, if the question says find the 3 smallest positive integers, there must be a solution, right? If this is true, so this is if and only if X exists, I guess I'll say. So there will exist an X there that solves that congruence if and only if the GCD of A and N divides B. If it's true that there is an X, then there's actually this many mutually incongruent solutions in mod n, right? So you can have more than one solution to, I mean, it doesn't work the way real numbers work, right? If I give you AX equals B in the real numbers, then there is always one solution for X, right? Which is just that, assuming A is not 0. So, but that's not how congruence theory works. In congruence theory, you can have many different correct answers to a linear congruence. And so there's this many mutually incongruent solutions. I think, well, what do you guys think could be the first thing we might want to do here? Based on everything I've sort of previewed this problem with.
Find the GCD.
Yeah, exactly. I would want to know, does it divide B? It probably does. I'd like to know what it is, so that I can at least start making some progress on this. And so let's find the GCD of these numbers. And again, I don't want to just do this numerically in my head. I want to actually work it out. So for the solution, I would take 301, right? You should show your work here. If you just tell me, oh, the GCD is equal to 7, I won't be too happy with that, okay? Because that would need some more justification. So let's write out the details. What you have to do is divide 140 into 301. You see right away it goes in there 2 times, which leaves you with a remainder of, I believe, 21. Okay? And then we move the 140 to the left side, and we divide that by 21. And so 21 goes in there, let's see, is it 6 times, I think? 6 times, leaving me with a remainder of 14, I think. Okay. I'll bring scratch paper to the test. If you need to like scribble some of these little calculations down on the side, you'll be able to do that. Next, I take 21, I divide it by 14, and I get a remainder of 7. And then I take 14 and I divide it by 7, and it goes in there 2 times, and now there's no remainder. So what is my GCD? It's the last non-zero remainder that you obtained in this process, which is 7. And you can check very quickly that 7 does divide 133. So that's good to know that. And then that means there will be 7 non-congruent solutions or mutually incongruent solutions to this congruence in mod n, right? Does anybody have a suggestion what I might want to do next? Now that I know that there's a solution. Okay, one choice, it's actually not what I'm going to do, but one choice would be to start from 7 and back substitute, running this, I refer to it as running the Euclidean algorithm backwards, right? And that would be fine. In that case, you're sticking with the universe of mod 301, right? Which is a relatively larger mod than we actually need to work in. Because what we now know is that 7 divides 140 and 301, because it's the GCD, and it divides 133. So is there another thing that we could do that would cut the size of these calculations down for us? Yes. Divide through by 7. Yes, we can divide through by 7. Thank you, guys. And just replace this with a smaller congruence. So let's do that. So divide through by 7. Again, you don't have to do it this way. If there's anybody out there who prefers to just stick with the original modulus, that is fine. But I like to reduce the numbers down. If I divide through by 7, I'm going to get 20x congruent to, let's see, when you divide 133 by 7, you get 19. And then this would become mod. And if I divide 301 by 7, I believe I'm going to get 43. Okay, so now I'm getting 43. Okay, and now, because we divided through by the GCD of A and N, now the GCD of the new A and the new N would be 1. Meaning that there would only be one unique solution to this system in mod 43, right? So there'll only be one unique solution. There would have been 7 unique solutions relative to mod 301, but now there will only be 1 here. But I technically, to find that one solution, I do need to run the Euclidean algorithm forward and backwards, unless, like in this case, maybe you think you could just eyeball it. There's only 43 possible values of x, but I don't think it's that easy still. I'm going to be trying really hard to not make it that easy to just guess the answer. So I want to see everybody showing the knowledge of the material. So let's run this Euclidean algorithm with these smaller numbers. I'm going to start with 43. When I divide it into 20, it goes 2 times, and there's going to be a remainder of 3. Okay? Then I'm going to take the 20, I'm going to divide it by 3. It goes in there 6 times with a remainder of 2. And then I'm going to take the 3, dividing it by 2. It goes in there 1 time with a remainder of 1. And now we have for sure obtained our GCD. And I'm going to run this one backwards now. Okay, so that's the forwards application of the Euclidean algorithm. So now let's go backwards. 1 is equal to 3 minus 2. And we're going to replace the 2 first. Okay, so always replacing the smaller number first. The 2 becomes 20 minus 6 times 3. And if we simplify that, that's 7 times 3 minus 20. So I like to do my simplifying over on the same line as where I've been writing. Okay, and now I have 7 times 3, but I'm going to take the 3 and replace that one with 43 minus 2 times 20. Okay, and then we still have minus 20 on the end of that as well. And I think we're just about there. This becomes 7 factors of 43 minus, let's see, 7 times 2 is 14, but that's a negative 14, and minus another one is actually minus 15 factors of 20. Okay, so running the Euclidean algorithm backwards, we discover what the sort of solution to the corresponding Diophantine equation is. And what you should do now, guys, is just take this result and just reduce it in mod 43, because that's the mod we're concerned with, right? If I reduce this in mod 43, 43 becomes 0. So in mod 43, it's a 1 equivalent to 20. I'm keeping the 20 because the 20 is here, right? Times negative 15. And so now you can see that, I guess I need just a little bit more room here, guys. What you can see is that 20 times negative 15 is congruent to 1 in mod 43. Now, I didn't want that. I wanted to find an x such that 20 times x would be congruent to 19 in mod 43. So far, did you notice the 19 has not shown up anywhere, right? So that b value, the b value on the right-hand side of your linear congruence doesn't really get into the action until the very last step now. And what you have to do basically is you have to say, oh, well, this was a 1. I need it to be a 19. So let's multiply through by 19. It doesn't change the mod. Okay, so I'm going to keep mod 43. And I'm changing that 1 to a 19. So what I'm doing here, guys, is I multiply through by 19. Okay. One thing you just have to be a little careful with, when you multiply the left side by 19, just make sure that you put the 19 with the negative 15, not with the 20. Because you see, you want to keep the 20. The x should have all of the rest of what you see there. So the 20 should stay here, and it should be negative 15 times 19. This part goes together. Okay, and that one, admittedly, you're going to have to do it by hand without a calculator. I did that and I got negative 285. So this would be for x, negative 285. Is everybody with me so far? I'm still not done, but that's at least a solution for x. 19. By the way, one way to do this would be to just say, well, I'm going to take 15 times 20. 15 times 20 is 300. I can do that in my head real easily. And then I just have too many factors of 15 because I took 15 times 20. I really only wanted to take 15 times 19. So you take 15 times 20. I honestly do mental math this way all the time. 15 times 20 is 300 and subtract 15 because you had one too many factors of 15 there. So that gives you 19 factors of 15 being 285. And then there's a minus sign there. Now, the question asks us, at this point, you would get 80% of the problem pretty much. But the question does ask for something different. It says find the 3 smallest positive integers. Any thoughts on how we're going to do that? In mod 43, right? In the world of mod 43, 43 is just like 0. So you can add and subtract 43 all day long without changing anything. So the brutally painful way to do this would be to add 43 and then add 43 again and then add 43 again because you're trying to get positive numbers. So you'd have to add 43 a bunch of times, right? The other way to do it is to kind of go back to your chicken scratch of calculation paper over here. You just do it over here and just take the 285 and divide it into 43. Okay, because you want to know, well, how many factors will there be of 43 inside of 285 that I really want to add? So this goes in there. You can pretty quickly figure out that it's going to be, I think, 6 times. 18, 258, right? So it goes in there 6 times with a remainder of 27. Yeah. And it's really the remainder that you care about. It just means that if you add 43 6 times to negative 285, you'll bring it up to negative 27. I'm kind of ignoring the minus sign when I do this calculation. I didn't include the negative at all. And we're still not happy with this answer because it's still not a positive integer. So now I could just add 43 to this one, right? So I could add 43 to negative 27, and that should give me 16. And if I then add 43 more to that, because it says find the 3 smallest answers, so 16 plus 43 would be another correct answer. And then 59 is correct, and we can add another 43 to that. And if we add another 43 to that, I think we get 102 as a third correct answer. Does that look right? You should tell me if this is actually at this point, the correct answer is just these 3 numbers. It's not mod anything. Because this says find the 3 smallest positive integers. Actually, it's an interesting question. If I ask you, let's say I have mod 8 and x is congruent to 5 and mod 8. If I ask you, well, is that solution positive or negative? Is that value of x positive or negative? I would argue that if you're trying to ask a question like that in a mod n scenario, it doesn't even make sense. Because 5 is the same as negative 3. So it's not positive or negative. There is no sense of positives and negatives in modular universes. So you wouldn't be saying, oh, well, this is in mod 43 anymore. Now you're just listing these answers. Okay, so it kind of makes sense. Anybody out there in Zoom is also welcome to jump in if you've got questions. I see that people have been writing in the chat, but I have to be honest with you, I can't really see the chat. So if you need to ask me a question, just unmute yourself and get my attention. Also, the other thing I wanted to say is if you do all of this right, but you just make a crazy computation mistake, and maybe you just don't add 43 correctly or something here at the end, I probably won't even bother you about that. I mean, maybe I would take off 1 point if it was something that was going to affect the whole problem. But I'm going to be pretty gentle on calculation errors. Like if I can see, oh, they're doing the right thing, but then somehow they just get the wrong remainder here, right? So instead of 27, if you got 26 or something, and you put that here, then of course your answer is wrong. But the vast majority of your knowledge is already being demonstrated, and I'm going to give you credit for that. So I wouldn't worry too much about that. If you have time, of course, it doesn't hurt to try checking your answers. Now, this would be a little bit hard, like 16 times 140, and then subtracting 133 from that to see if it's a multiple of 301. You could do all of that without a calculator, but it would depend on just if you had extra spare time for that. Okay, so I like to see people checking their answers in number theory, but it's also a matter of just the time issue. And so I do get that, and there's not always enough time to do all that stuff. Question, Sergio?
Yeah. So could we have this multiplied 43 times 70 and then subtracted 285?
Yeah, if we did 43 times 7, we would have gotten a number bigger than 285. So then when you subtract it, you would get a remainder that was negative, but of course I'm doing a sign change here. It would have worked. Yeah, that would have worked. Yeah. I was just trying to keep negatives out of this stuff here. But yeah, that would totally work. Okay, let's move on. Got some more problems I want to show you. Let's go to number 4 over here. This is also going to be computational. And it's also going to be with congruences. You can imagine there's going to be a lot of congruences on Tuesday. Right? We've been doing tons of congruence theory. So that would not surprise anyone. But this time it's going to be an entire system of congruences. So let's do this. Number 4. Right? Number 4, find 4 different integers x with, and now I'm going to give you a system. So x is congruent to 56 modulo 100. And then 7x is congruent to 32 modulo 80. So I've got 2 congruences here, and I'm looking for 4 different integers x that satisfy that system. Okay. Again, there's always a question about whether the system even has any solutions at all. All it takes for me to bring that into play is I say, if possible, find 4 different integers x, right? Then you have to think about whether it's possible or not. Does anybody remember the condition for when you have a system of congruences, when you would be able to say if there was a solution or not? The way this was presented in the lecture was something like this. X was congruent to A mod n, and X was congruent to B mod M. And the condition was that the GCD of M and N, right, needs to divide the difference of A and B. So this is another if and only if. So this has a solution if and only if, and then this is the condition here, if you guys remember that. So we talked about this. This was in the section on variations of the Chinese remainder theorem. Variations of the Chinese remainder theorem. The Chinese remainder theorem, guys, when I see a system of congruences, whenever I see more than one congruence in a system of congruences, boom, my head should be thinking CRT, right? Chinese remainder theorem. And if you write that on the paper and you don't write anything else down, I can at least give you a little credit for, they know that this is about the Chinese remainder theorem. So you should write that down. However, we cannot just launch into the Chinese remainder theorem right away. There's 2 reasons that we cannot do that. Can somebody tell me a reason why I cannot just immediately start applying the Chinese remainder theorem here? For the Chinese remainder theorem, the moduli must be pairwise relatively prime, which these are not. Okay, so we cannot use the Chinese remainder theorem. And is there anything else that would be wrong that would prevent us from immediately using the Chinese remainder theorem here? What else is kind of out of sync with the 7? Yeah, in front of this second congruence, I have a 7 here. And in fact, because of that, I can't even use this condition yet. Because I don't actually know what the A and the B are. I mean, I know that I have a 56 and a 32, but that 32 is going to change as I get rid of this 7, right? So the first order of business should probably be to focus on the second congruence by itself and get that 7 out of the way. I do kind of know just by looking that the 7 and the 80 are already relatively prime. And because 1 divides 32, that this is going to have a solution, but I need to get rid of that 7. Again, the numbers are just big enough that I don't think it's super easy to eyeball the answer, right? So probably with the, I mean, it's not super easy to eyeball how to get rid of the 7, right? Like the idea is, oh, I'd like to multiply the congruence through by something. But what you'd be multiplying it through by is something that should cancel this 7 in the world of mod 80. And I can't just eyeball that. Like, I can't just see it. So this is another case where, now I'll start solving it, we need to use our Euclidean algorithm, right? So we take 80, we divide it into 7. When we do that, it goes in there 11 times with a remainder of 3. And then we take 7 and divide it by 3, it goes in there 2 times with a remainder of 1. All right, so now we've got 1 here, and I'm going to start running the Euclidean algorithm backwards. So 1 is equal to 7 minus 2 times 3, and then I'm going to replace the 3 with 80 minus 11 times 7. Okie dokie. And that is going to be 23 factors of 7 minus 2 factors of 80. I'm going a little faster this time just because we've done this already once, and I don't want to get us too bogged down on the calculation of that. But this is the equation that's going to work. By the way, if you ever get nervous that you may have made a mistake, you can always just multiply this out. 23 times 7, oh yeah, that's 161. 2 times 80, that's 160. If I subtract them, yes, it does still equal 1. So you can always kind of just do a quick self-check on that. Now I'm going to pass to mod 80. And in the universe of mod 80, now we see that the inverse of 7 is actually 23. So 23 was the magic number that we needed to have. And so that's, so 23 times 7 gives us 1, but we need 32. So I'm going to, just like before, I'm going to multiply through by 32. And I'll get 32 is congruent to 7 times, and now here's the x value, 22 times 32. Sorry, 23 times 32. And this is happening still in mod 80. Always put that mod there, guys. I don't mind if you draw an arrow and it's going all the way down the page. That's your mod 80. But if you don't have a mod, if somebody writes this on the test and there's nothing to tell me what the mod is, I basically can't give credit for it. Like, I don't know what it means. So be sure that you're being careful about what modulus you're working in as you're working on something like that. Now, in this case, we would need to figure out 23 times 32. Let's just use a little scratch paper here. It's not too bad, actually. 23 times 32 is 736. So this is 736. And that's how we're going to simplify the second congruence in our system. I'll come over to this next board to kind of write down what it's going to turn into. Everybody so far so good? Okay, so far so good, I hope. So what we have then, guys, is we still have x congruent to 56 modulo 100. And now we have x congruent to 736 modulo 80. But as you might guess, I'm going to reduce 736 in mod 80. I might notice, for example, 720 is a multiple of 80. 80 times 9 is 720. So I can subtract 720 from this right away, and it leaves me with just 16. Okay, so my new system, I am going to write it down one more time. X is congruent to 56 modulo 100, and x is congruent to 16 mod 80. We've at least taken the second congruence from the original system and replaced it here. Guys, this would be a 10-point problem. This would be a big problem because we've already done a fair amount of work and we haven't even gotten to the part about solving this system as a system. Still cannot use the Chinese remainder theorem because of the mods not being pairwise relatively prime. What we can do is double check that there will be a solution. So the GCD of 180, the greatest common divisor, I believe, would be 20. Yeah. I'm just going to see that. And then if I take A minus B, 56 minus 16 is 40. And sure enough, 20 divides 40. So this condition here, this condition over here is just verifying that there will be a solution. Okay. And it will be a unique solution modulo the product of the mods. Okay, or sorry, the LCM of the mods. So if you take the LCM of 180, you get, I believe, 400. Yeah. So the LCM of 180 is 400. Yeah. Does everybody know how to find the LCM of two numbers other than just kind of brute forcing it?
A times B divided by the GCD of A and B.
Okay, one way to do it, that's a great idea, is you just multiply the two numbers together. In this case, that would be 8,000. 8,000 divided by the GCD, which is 20, gives you 400. So this is not really part of solving this problem, but just a quick little recall, as long as we're thinking about it. Recall, guys, that if you have two numbers A and B, that their product is the same thing as the LCM of A and B times the GCD of A and B. Yeah, so that is definitely a true statement. I'll let you chew on whether you think you could prove that or not. I'm certainly happy to talk about how to prove it. I think the best way to prove this is to write prime factorizations of A and B separately, and then look at which primes are common and to which powers. It's actually not so difficult to do it. But I don't want to distract from this problem right now, so I'll come back to that later. But yeah, this is a good way, guys. If you're trying to figure out what's the LCM of two numbers, you can first find the GCD of those two numbers by using the Euclidean algorithm, and then divide that into the product of the two numbers. That's a good formula to know. I did share this at some point, didn't I? I think so. I just couldn't remember when. It's been a while. Okay, so now we've got our system here. We're going to get solutions that are unique modulo 400. Now the question is, how do we get those solutions? So there's a couple of options for how to do this. One way to do it is to simply memorize the formula that I gave you. So I am going to just remind you here that this GCD can be referred to as D. And then this 40 is just the A minus B. We have the N and the M, which is the moduli, and then the T. T is simply A minus B over D. So this was supposed to for sure be an integer, which it is. And then we just need an S and a T, which comes from writing the GCD as a combination of the two numbers. So do you remember this? So if basically D is of the form, 100x plus 80y. That's just the usual. I'm sorry, actually in the notes when I was covering this, I believe I called those numbers R and S. Okay, so this is in the lecture on this material. I kind of went over all of this. So for some R and S here, we have that equation. So this is a little something. I'm trying not to give you an overload of stuff to memorize, but this is one place that would be probably worth it only because there's so many different letters. There's an N, there's an M, there's an A, there's a B, and now we've got a T and a D and an R and an S. Okay. You have all of those letters. In this case, the D was 20. And I bet you can just look at it without having to actually do the Euclidean algorithm on 180. Can you just give me, this would be something I would accept it. Like if you just said, here's R, here's S, I would take that. Because I believe that everybody in this class could figure out numbers R and S that would make this equation true. Which would be what? Yeah, 1 for R and -1 for S, okay? Again, during the exam, if you get something like this, you're like, I don't know, do I need to show my work or is that an obvious calculation? You can come up and ask me about it. If it's pretty obvious, I'm gonna be okay with that. Like if I don't want it to be obvious, I'll make the numbers big enough that you can't do it in your head. This one, you can do it pretty much in your head as a mental arithmetic calculation. Anyway, the solution for X is, and we wrote this down in class, this is what you might need to memorize. It is A minus nRT. So I would suggest there's not a huge amount of stuff to memorize other than the proofs that you're learning, but this one would be worth making sure that you know. When you're solving a system of congruences where the mods are not relatively prime, this is your solution. So the A value on this congruence is 56, and then minus the N, which is 100, the R was 1, and the T was 2. Okay, so we have all those values that we've worked out, and that comes out to -144. This one, it wouldn't be the worst idea in the world to just come back to your original system and check that that X works. -144, is it congruent to 56 in mod 100? It sure is, right? And -144, is it congruent to 16 in mod 80? It sure is, right? You subtract the two numbers, you get multiples of whatever that mod is. Okay, so it's easy to check that answer. And so this would be a solution. Now, the problem is asking for 4 different integers that would also be solutions. So what would be a way to get 3 other solutions? This is one solution, and it's, yes. Yeah, the solution to the system is unique modulo 400. So guys, you can add and subtract 400 all day long without actually changing the validity of the solution. So I would probably just, in this case, probably just subtract 400s so that I don't even have to do anything hard with my head as far as calculations. So just, you could write down those 4 answers there and it would be totally fine. Okay. Any questions about this one? I did want to review how to deal with systems of congruences where the moduli are not relatively prime. And this is important to know, and you do need to know, well, what is R, what is T? It goes along with S and D and all these other letters. So there's about 7 or 8 letters there that you have to kind of know everybody's role in that setup. Okay. So far, so good. Okay, you guys all know my favorite sport to play. Have I told you that? It's basketball, believe it or not. Even though I'm not that tall. But I like to shoot from outside. And when I shoot from outside and I make the basket, I get 3 points. This is a 3-point shot. And I thought, well, maybe I should make a problem that creates even more of an advantage for somebody who's shooting from outside. So I did it. I have a problem for you. This is a word problem about basketball. So I'm going to do another example, number 5. Okay, hopefully you'll like this. So there is a new scoring system for basketball. Got a new scoring system for basketball, namely field goals are worth, instead of 3 points, I want them to be worth 4, 6, or 9 points. And Dr. Annan won the last game by scoring. Dr. Annan won the last game by scoring 137 points on 23 field goals. Just a little bit of writing for this, sorry. Kind of like word problems time to time. So there was 137 points scored in total on 23 field goals. Every field goal was worth either 4 points, 6 points, or 9 points. The question is going to ask you to make a list of how many of each type of field goal did I make. Okay, so how many field goals of each type did he score? I get kind of bored with just seeing a congruence is written down and it asks to solve it, or the Diophantine equation has to solve it. So this puts it into a word problem. We had a couple like this. There was a problem with a movie theater, men, women, and children going to watch a movie. And so like, how many people were at that movie? What kind of question is this? What does this have to do with? What topic that we've covered would this be related to?
Is the one when you find the regular standard formula for like x is equal to x naught plus b over dt and y equals y naught minus a over dt?
Okay, so Kim's got the equations for us, but I'm still waiting for I'm waiting for those magic words of what is this, what kind of a problem is this about? It's not congruences. It's not congruences. What is it? Yes, this is Diophantine equations. This is Diophantine equations. And you'll see that in a second when we start solving it. You'll be like, oh yeah, of course that's Diophantine equations. So I'll just go ahead and write that here. And so yeah, this is going to involve Diophantine equations. The only thing is we have to set up our notation, right? So in other words, if I want to write down the equations, I need to have variables in those equations, and those variables should hopefully be related to what this information is telling us. So what do you suppose we're going to want to have variables for?
The amounts of each type of field goal.
Yeah, for each type of field goal, there's 4-point goals, 6-point goals, or 9-point goals. I'd like to know how many of each there are. So let's let X be the number of 4-point goals. And then we could use Y. Again, you don't have to use X and Y. You could use A and B or other letters as well, but I'm just going to use X and Y for now. And Y could be the number of 6-point goals. And then Z could be the number of 9-point goals. Okay. And can you tell me what equations we would have that involve those variables that we've just created?
X plus y plus z is equal to 23.
Okay, the total number of goals, that's really good. 23 field goals total. That's just x plus y plus z, just adding those up. It should just be 23, right? That's certainly one equation that we would need. Is there anything else that we can say? Let's see, I scored a total of 137, right? That's going to be broken down according to how many of each of these I scored. So for every 4-point goal, right? Well, that would be x times 4, right? Because I'm getting 4 points for each of those, right? And then on the 6-point goals, that's going to be 6 times y. And then I get for the outside goals, the 9-point goals, I would score 9 times z points, and that would be adding up to 137, right? It's going to look like that. Okay, so that's getting it set up. And now, if you didn't see it already, now you're probably more inclined to recognize it. Like, oh, this is Diophantine equations. Any thoughts about what I need to do with this system here?
Bring your x and y over to the other side and plug in z equals 23 minus x minus y.
Yeah, we can remove one of the, thank you, Kim. We can remove one of these variables by substituting it into the other equation. So I'm going to take the one on the bottom and I'm going to replace z by 23 minus x minus y. Okay, so that's an easy way to make the substitution. I'm trying to avoid any fractions as much as I can for as long as I can. So let's go ahead and do that. If I simplify this left-hand side, I actually have negative 5x's and minus 3y's. And then on the other side of the equation, I'm going to take the 23 times 9 and move it to the other side. 23 times 9 is 207. I'm going to be subtracting that from 137. And because of that, I end up actually with a negative 70. Okay, so we have negative 5x minus 3y equals negative 70. And I'm just going to multiply through by a minus sign so that I can write down my nice, simple Diophantine equation here, which is that 5x plus 3y adds up to 70. And from here, well, remember, not all Diophantine equations have solutions. You have to, again, check. So if we have ax plus by equals c, that's only going to have a solution. Just to remind you again from this section, we take the GCD of a and b, it has to divide c. As long as it does, you'll be able to solve for x and y. And the way you do it is what we've already seen a few times tonight, which is I have to run my Euclidean algorithm on the a and the b. And these are really small numbers, so we should be able to do it really quickly. So 5 is obviously relatively prime to 3, so you're not too concerned that it's going to divide 70. But just to write it out, we would divide 5 into 3, getting a quotient of 1 and a remainder of 2. Then we would take 3 and divide it into 2, and we would get 1 with a remainder of 1. And I have to run that backwards now. So 1 would be 3 minus 2. And so replacing the 2 with 5 minus 3. I'm going kind of quickly through this part. We just get 2 times 3 minus 1 times 5. And this is all equal to 1. If I could make a suggestion here, the way that the terms are written on the right side is not lining up nicely with the order of the coefficients in the original congruence. To really minimize mistakes on this, I would recommend getting them lined up. So we have a 5, and you look here, well, what is 5 multiplied by? It's negative 1. And then plus 3 times 2, and this is equal to 1. And I like to do that because now, well, obviously I want to create a 70 on the right-hand side. I'm just going to multiply through by 70. And I'm going to be able to very quickly absorb the factor of 70 into the x and y values. I don't want to mess with the 5 and the 3. So you should put those in the correct order so that it makes sense. Okay? So far, so good. At this point, I'm just kind of reviewing this. At this point, we do have an x naught value and a y naught value in the notation that Kim reminded us of earlier. We actually do have an x naught and a y naught here. And so this is another thing that is worth perhaps just memorizing this formula. X is going to have many correct values. Remember that if there's a solution to a Diophantine equation, there will be infinitely many of them. So the x is equal to x naught plus b over d, and the y is equal to y naught minus a over d, and both of those are times t. Yeah, times t. So let's just plug in all the numbers that we have so far. The x is equal to x naught, which was negative 70. And then the b over d, okay, so you have to remember the b is actually this value here, right? So this is the a and the b. Right, so the b was 3, and d is just the GCD, right? So d is just 1. I'm sorry, I did not write that in the right place. The 1 is this thing. Yeah, just the GCD. So x is equal to negative 70 plus 3t, and y is equal to 140 minus 5t. That look okay? So in other words, one way that I could win this game with these rules is I could make, this many 4-point goals and this many 6-point goals. But we quickly realized that because it's a physical problem here, we're not expecting negative values for x, y, and z. The number of 4-point goals, 6-point goals, and 9-point goals should not be negative. They could be 0, but they should not be negative. So let me just kind of add that here to the side, guys. This x value should be always at least 0, and the y value should always be at least 0 in order for it to even make sense, right? It's not going to make sense otherwise. And from there, I can get some conditions on t. So if you just look at this first equation, and sorry, I'm kind of going from right to left here. If I solve this for t, on this first equation, t is at least 70 divided by 3. And on the second equation, if I do something similar, I'll find that t is at most 140 divided by 5. And that actually creates a range of t values. Let me move this camera a little closer. That's going to create a range of t values that would be acceptable as answers to this question. So 140 divided by 5, that one I can do really quickly. I think it's 28. Okay, so t is at most 28, but then it's at least, let's see, 70 divided by 3 is like 23 point something. But remember, guys, t is supposed to be an integer. So if I get 23 point something here, so this is 23 point whatever. I don't even care what it is, but it's not just 23. So t is actually greater than or equal to 24. So it's at least 24. It's at most 28. Yeah. And so that gives you actually several ways that I could win this game with those details, right? So if, for example, if t is equal to 24, let's just see. If t is equal to 24, then x, so if t is 24, and I plug in here, 3 times 24 is 72, subtract 70, so that means I got 2 4-point goals. And then at the same time, if t is 24, and I plug 24 into here, 24 times 5 is 120. 140 minus 120 is 20. So that would mean that I scored 20 of the 6-point goals. And then remember that z is equal to, z would be equal to 23 minus x minus y. So I have to subtract from 23 what I have so far, and that actually only leaves me with 1. So I would only have one 9-point goal. Now the thing is, these t values were set up to make sure that x and y were greater than or equal to 0. But you also need to make sure that the z would be greater than or equal to 0 also. So if you work out values of x and y that add up to more than 23, those are outcomes that are also impossible, right? Because every one of these x, y, and z variables cannot be negative. Okay, so I don't need to write them all out. Maybe let's just do one more just to kind of make sure everybody's got the feeling of it. But there's 5 of them to write down, and maybe we can just do 2 of them here. If t is equal to 25, you can check real quickly that x would be 5. And at the same time as that, the y would be, let's see, 5 times 25 is 125, so this becomes 15. And that means that z is 3. So I could also win the game by scoring 5 4-point goals, 15 6-point goals, and 3 9-point goals. And so you could keep going like that all the way to the end. It's not very likely that I would ask you a problem where you have to write them all down. Maybe I might just ask you, give me 2 different ways that Dr. Anna could win the game with this information. Right? And then you just pick 2 values of t, write them down. That would be that. I don't need to see. I'm not the type of person who asks the same question on the test again and again. I will probably only want to see you show me how to do stuff one time. Okay. So far, so good? All right. Questions. So we've done a few computational examples. What have we seen so far? We've seen Diophantine equations. We've seen linear congruences. We've seen elementary results on GCDs and LCMs. I feel like there's still a lot more. Okay. Well, that's why I have 5 more problems still. Still have 5 more problems. But these, I think, well, if nothing else, these are faster for writing them down at least. So let me go ahead. Is everybody ready to go to another example? How are you feeling so far? You're like, oh my God, I'm really going to need to study hard? Or are you feeling like, okay, I remember that. It's familiar. The idea of the review session isn't you're not going to walk out of here thinking, oh, now I'm ready to take the test. No, what you're supposed to be doing is saying, okay, here's what I feel solid on. Oh, that was something I need to review again, right? Just kind of trying to poke your brain about different topics, and then hopefully you're making some notes. Oh yeah, maybe I do need to review Diophantine equations, or whatever it is for you that is a sticking point. Now you'll have a little bit of a heads up about something that maybe you need to review. Okay, so let's try this one, guys. Let's try to prove. I'll go back to something that's proof-based. Let's try to prove that for all n in the positive integers, I'll write that as z plus, 27 divides 2 to the power of 5n plus 1 plus 5 to the n plus 2. And this is asking us to prove this for all values of n. Any thoughts on how we could go about this one? This is a lot easier problem to write down than the last one was. Pretty sure we had some homework like this.
You can find 2 to the power of 5n plus 1 plus 5 to the power of n plus 2 mod 27.
Okay, so one
Or-
solution is to work in mod 27.
And then
Let's-
after that, you can split it because 27 is 3 to the power of 3. So you can do it in mod 3.
So if something is, okay, so let me start from the beginning. You are trying to show, so this actually is not the way that I necessarily would think to do this, but it should be okay. But you should be working in mod 27, not in mod 3. Because if you work in mod 3, you're only going to prove that something is divisible by 3, not that it's divisible by 27. So the modulus is going to need to stay as 27. But I could do it this way. So I could just take this expression and I could try to reduce it in mod 27. By the way, in mod 27, what would I be trying to reduce it to? I'm
0.
going to turn this into a congruence problem. What should I be proving that this thing is congruent to in mod 27?
0.
0, right, exactly, because I'm trying to prove that 27 actually divides that number. So I would be trying to prove that that becomes 0. Okay, so let's see.
Dr. Annan,
Yes.
is the power on the 5n plus 2 or 2n plus 2?
Oh, I'm sorry. The power on 5, I am so sorry. That is supposed to be n plus 2. It's
Okay.
hard enough to see the screen in Zoom, and then when I type it wrong, when I write it wrong, it makes it even harder. Yeah, that's what it should have been. Thank you.
Thank you.
Yeah, you bet. Okay, any thoughts on how to simplify what I see on the left side here?
You can do
Rewrite.
2 to the power of 5n times 2.
Yeah, I would just work with the laws of exponents here, right? So this is just, 2 to the 5th to the nth times 2. That's the first term. And then I'm going to give myself a little more space here. Plus 5 to the n times 5 squared. So this is just using high school algebra of exponents. And this is perfectly fine. I would want to see you write mod 27 here. You can just draw an arrow if you don't want to keep writing that all the way down the paper, that the whole thing is going to be in mod 27. Okay. And we're hoping to get 0, right? We're hoping to prove that 0. When you're doing a proof like this, guys, I'm assuming everybody has done some proofwriting in other places as prereqs for this class. You should not be writing anything else down on the left side. Let's just make a chain of statements on the right side, working our way down, and hopefully by the time we're done, we have a 0 down there, because that would be equivalent to what they're asking us. Okay? Anything you want to tell me about cleaning up the right-hand side, what we have so far? Or simplifying it further?
2 to the power of 5 is 32.
2 to the power of 5 is 32, and I'm going to reduce it in mod 27 right away. So in mod 27, 32 becomes 5. So that becomes 5 to the n times 2 plus 5 to the n times, and actually 5 squared is just 25. So I could just change that to a 25. And
5 is also the same as -2.
It's also the same as -2. Yes, the other thing you can do here is you can factor out 5 to the n. And of course, that leaves you with 2 plus 25, but 2 plus 25 is 0. So this is 5 to the n times 0 in mod 27. Okay, does that seem all right to everyone? Would there be any other way to do this problem? Because I think we did these kinds of problems even before we were starting to talk about modular arithmetic. Can anybody think of another approach to something like this, just in case? Nice to have more than one way to think about it. Pretty sure you all did it because it was in the homework.
I don't know if it's the best way, but induction on n.
Yeah, exactly. We did this kind of problem by induction on n back in the beginning of the semester. I mean, this problem was kind of more or less from chapters 2 and 3. It was not something we've done more recently. So another alternative, I'll just go fairly quickly through this one. I like the solution we just presented. It's really nice, but just in case you wanted to, maybe you did maybe you'll see a problem where you can't do it this way. Or maybe I might even ask you, I might even say, don't use modular arithmetic to do the problem. I don't like to do that usually though, to be honest. I usually like to let people do whatever technique they want. But let's say induction on n. And that always involves starting with a base case for the induction. And this is n values that are greater than 0. Well, they're positive integers. So the base case is going to be n equals 1. And so you just have to check, is it true for n equals 1? Well, 27 divides 2 to the power of 6 plus 5 to the power of 3. That's what you have to make sure you believe. And it's easy to do that. This is 64, and this one is 125. And if you add 64 to 125, you get 189. And it's pretty easy to see that that is divisible by 27. It goes in there exactly 7 times. So 27 times 7 is 189. And so this is just a little calculation for n equals 1. By the way, this would have been true also for n equals 0. So if you didn't like numbers that are quite that big, you could prove it for n equals 0. I could have made this question account for n equals 0 as well. I just didn't happen to do it here. So, but yeah, so you would do that, and then for the induction step, oh boy, I probably don't have enough room right here. Let me come back over here. For the induction step, you assume that it's already true for some fixed but arbitrary n, and then you try to prove that it follows that the next value of n is still true. So for the step, as I like to call this, the induction step, we assume, do you guys like to assume the statement as it's printed and prove the next value of n, or do you like to go backwards and assume the previous n and prove this one? They're both equally valid.
I usually see k plus 1.
You like to go from n to n plus 1? So, okay, so if we were doing it that way, and this is certainly fine, you would just assume exactly what you see here. So you just take what's given right in the question and you make that your assumption. And then you try to prove that the next value of n also still works. By the way, so from this assumption, we can say that there exists, I don't know, a k in the integers. There exists some integer k with 2 to the power of 5n plus 1 plus 5 to the n plus 2 equals 27k. So you could assume already that 27 divides the given statement that was in the question itself. And then what you're going to need to do is prove the next, the n plus 1 version of what's given here. So what you would be doing is you would be taking 2 to the 5 times the quantity n plus 1 and adding that to 5 to the power of n plus 1 plus 2. Okay, so it would look like that. And so if you simplify that, that's 2 to the power of 5n plus 6 plus 5 to the n plus 3. And of course, these are the wrong powers of 2. compared with what we just assumed in the box right there. So the powers of 2 have now gone up pretty substantially. What you're going to want to do if something like this comes up, what you need to do is you need at all costs, you need to get this expression to look as much like this expression as you can. So what I would say here, for example, was, oh, there's 5 powers of 2 before we get to the 5n plus 1 exponent, which is the one we want. Okay, so I would pull out 2 to the 5th. I would do the same thing on the second term. I'd pull out a 5, and it leaves me with a 5 to the n plus 2. So that's just doing algebra only, but it's a key step. Okay, any thoughts on what I might want to do from there?
You can rewrite 5 as 4 plus 1.
I could write 5 as 4 plus 1, but I don't have a 4 that is related to any of the work on this board. So when we rewrite one number in terms of other numbers, it should be done in a way that is going to be helpful to use what we already have. So like if you told me you were going to rewrite the 5 using a 27, that I would be more excited about than rewriting a 5 as a 4 plus 1. So I do like the idea of replacing the numbers that you see here, but I want to do it in a way that makes the most sense. Brian?
So 2 is 32, and then you get to 27 plus 5.
Okay, the 2 to the 5th is 32. I would use that and I would write it as 5 plus 27. Exactly. So this is going to be probably the best way to go, or at least it's going to be a pretty good way to go, like that. Okay, absolutely true. Okay, and now I need just a little more room. So does that make sense? Instead of breaking the 5 as 4 plus 1, I'm breaking 32 as 5 plus 27. This is because 27 is, a star of the show of this problem, right? That's the number that we want to see. So what you could do from here, guys, is you could actually pull that term that has the 27 in it out in front, because you already know that that one is divisible by 27, and you won't have any problem with it. The rest of the terms that you have is a 5 times 2 to the 5n plus 1, and then plus 5 times 5 to the n plus 2, just like so. All right? And what do you suppose I'm going to do now?
Factor of 5.
Yeah, the second and third term on the right side has factors of 5. I love it. So I'll pull out that factor of 5. When I pull out that factor of 5, guys, on the last 2 terms, look what you actually have. You actually are left with what's in the box, which means you can change it to 27K. That's just the 27K that is in the box that we are starting with. And now I'm really happy as I see that I can pull 27 all the way out of everything here. Okay, so that's absolutely going to take us to the finish line because we're trying to prove that 27 divides this thing that we have, right? So 27 divides 2 to the 5 times n plus 1 plus 5 to the n plus 1 plus 2. So that's absolutely going to be a good way to go. Yeah, I like that one. The chain of congruences in mod 27 was probably the easier one, right? The first solution is just cleaner. It was much shorter. We didn't have to mess around with this induction, doing the induction step and whatnot. But it's nice to know that you can do these problems without the congruence theory at all. If you're willing to just plug away at it a little bit harder. Okay, I am going to come back over here and give you guys another example. Doing great. Everybody else? Oh, everybody out there doing great? Okay, fantastic. Let's do another one. So we'll go for a little longer here. It's getting close to 7. I'm not going to go too much over. Back when I was a grad student, I would do these review sessions for hours. I mean, hours and hours. As in, we had to take dinner breaks and come back. And my review sessions as a grad student were legendary. This is back when I was like 25 years old, so it was real easy. And even students that were not in my classes would be showing up to my review sessions because they heard, oh, this guy, he's a TA or whatever doing these review sessions. I wasn't even writing the test. I was just the guy kind of trying to help everybody prepare for the professor's exam because I wasn't a professor at that time. And so my students in my section, they would come to my review and then they would tell people who had a different TA, oh, you should come to those review sessions. And I had to reserve this big auditorium and it would go for hours. And I had all these problems. And I finally realized after a while that the only reason everybody was sticking around was because I kept doing more problems. If I would just stop, then we could call it a day. And everybody probably just wished that I would stop. So anyway, I kind of backed off from doing such long review sessions now because it's just, I don't know, it's just harder on me than it used to be to go that long. I'm definitely excited about the material, but that's why I reserved a second night for this. If I don't finish, I have about 4 more problems here, but some of these last ones are going to go pretty fast. So I may get mostly done with it before we're even out of time today. But I won't go super late because I also want to go get some to eat before I come back from my office hours. Yeah. So anyway, let's go on to number 7. I would like to show that 120 multiplied by 91 factorial is congruent to 1 in mod 97. So it's a real short, simple statement here. This time, there's no n in the problem, so we're not thinking about induction. It's just a straight numerical congruence that we're trying to verify. Does anybody out there think they have any idea what this has anything to do with?
Fermat-Little's theorem.
Sorry? What did you say? Wilson's theorem. Yeah, actually, this is Wilson's theorem. This is the one that has this factorial in it. So I wanted to remind you about the Wilson's theorem. And it just says that if you take a prime P, so if P is prime, then P minus 1 factorial is congruent to -1 in mod P. Okay, so that's one that you should make sure you know. I don't think that's one of the proofs on the list, but it's it's a consequence of Fermat's little theorem. We proved it using Fermat's little theorem, but this is certainly good to know, and it's relevant mainly because I see the factorial up there. Now, this has not been set up perfectly though, because if I want to actually apply this, I have to come up with my prime. What prime number am I probably going to be working with here?
97.
Yeah, 97, right? The modulus is 97. But the trouble with it is that, well, according to the theorem in blue here, this would mean that 96 factorial is congruent to -1 in mod 97. So that's okay, we can work with that. But it's not the right factorial, right? It's 96 factorial rather than 91 factorial. So what do you suppose I should do?
You can take out a 96 and 95.
Split up the factorial, right? So I can pull out 96, 95. This is another case, guys, where you probably don't see the whole solution right away, but you just go forward in faith, right? You say, okay, I know that I need to get that 91 factorial to show up. So I'm going to go ahead and put it there by splitting off the first whatever it is, 5 numbers from 96 to 92 out in front, and then the 91 factorial is showing up there. Okay, any thoughts on what to do from there? Brian?
On 97, right, 96 is -1, and that is -2.
Nice. So in mod 97, these values that we are looking at here, guys, 97, 96, sorry, 96, 95, 94, 93, and 92, they are just -1, -2, -3, -4, -5, right? And I'll leave the 91 factorial the same, and I'll leave everything else the same, but that is kind of nice. How many minus signs do I have on the left side? 5 of them, right? So that's a total of a negative, right? And then what's 1 times 2 times 3 times 4 times 5? That's 120. So negative 120 times 91 factorial is congruent to -1 in mod 97. Yeah, so this is just a neat little computation using the Wilsons there. And what's the only thing left I have to do? Yeah, multiply by a minus sign all the way through. It turns out to a plus and turns out to a plus, and I get exactly what I'm asking for. So that's why I said some of these last problems may be a little bit faster. A little bit faster. Okay. Let everybody take another stare down at that, and then we'll move on to another one. Okay, so any questions on that one? Just kind of wanted to get Wilson's theorem back into your head again. Let's come over here and try another one. Number 8. Here it is. Let's find the remainder. Find the remainder when 7 to the power of 2006 is divided by 3,800. Find the remainder when 7 to the power of 2006 is divided by 3,800. So these are pretty big numbers. No way that you're going to do this kind of in your head, probably, but obviously it should be something that we can reasonably do. So I'm really asking, what I'm really asking is what is 7 to the 2006 in mod 3,800? That's really what it's asking us for. This is going to take several steps. This is probably not just a little 10-point this is probably not just a little 3-point problem like this one probably would be. This is going to be a bit more because there's a fair bit we have to do here. But let's see if we can break it down. Does anybody have a good starting suggestion? Even if you don't know how to do the whole problem yet, what would be something kind of natural, but makes sense to at least do that much just to get the ball rolling on some idea here?
Split up 3,800 with its prime factors.
I would definitely want to do that, right? This one's actually not so bad to factor 3,800 because I can see 2 times 19, which is 38. And then all that's left after that is 100. And 100 is just 2 squared times 5 squared. So altogether, it becomes 2 cubed times 5 squared times 19. So I like the idea of doing that first. And any thoughts on how that can help me? Trying to find what 7 to the 2006 is in this mod.
You want to find where that 7 to the power of 2006 divide into 2 to the power of 3, then do the same for 5 to the power of 2, and do the same for 19.
Thank you, Kim. Did everybody catch that? I want to work in each of these individual mods separately. Okay, now if I'm going to do that, then I've got to be prepared that I'm going to need a Chinese remainder theorem. So this is a very, very common strategy, guys, is that when you're working in a modulus that's being broken down into primes, what you want to do is work with each of those primes separately first, right? So in other words, I would like to follow the suggestion here. I'm going to take 7 to the 2006, and I would like to work it out in mod 8. And then I would like to work it out in mod 25. And then I would like to work it out in mod 19. Those are my 3 mods, and I'm going to try to work them out in each of those cases, okay? Let's take them one at a time. So the idea here, guys, is let's take the one problem that they're asking us and break it into 3 easier problems, right? If I work in mod 8, the smaller the mod, right? The general rule of thumb is the smaller the mod, the easier it will be, right? The easier it will be. So what are you going to do to calculate 7 to the 2006 in mod 8?
You can rewrite the 7 as -1 to the
That's
power.
-1, right? Right. So guys, mod 8, can I use the Fermat's little theorem here? Heck no, right? I can only use Fermat's little theorem if the mod is a prime, right? Well, 8 is not prime. So I can't use the Fermat's little theorem, but I can, let me just kind of draw an arrow here. I can change 7 to -1. Am I also able to reduce the 2006 in mod 8? Does it work for exponents like that? It does not, right? It really does not. If I want to reduce the 2006, the main tool for doing that is the Fermat's little theorem, which is not available to me right now because I'm in mod 8. So I kind of have to live with the exponent being 2006. The nice thing, though, is that 7 turned into -1. And what is -1 to 2006 power? 1, right? So that's the first one. In mod 8, we get a 1 out of that thing. All right? Okay, let's try the next one. 7 to the 2006. Now I want to work in mod 25. This is a little bit bigger mod. Any thoughts on how that one might shake out?
7 to the power of 2 is 49, which is also congruent to -1.
Okay, so I'm going to take the 2006 powers. I'm going to follow Kim's suggestion and write it as 7 squared. This would be then raised to the 1003 power. Now, guys, we're not just kind of doing this randomly. Like, I'm not just like winging it here. I'm saying to myself, oh, 7 squared is 49. That's really close to 0 in mod 25, right? So if you can see that that's happening, then take advantage of the power of modular arithmetic. In mod 25, 7 squared is just -1. Because 7 squared is 49, which is -1 in mod 25. So this just becomes -1 to the 1003 powers. And what is that going to be the same as? -1, right? Because it's an odd power of -1. So that's just -1 in mod 25. Okay, great. So far, so good. We're getting each of these reduced. What do you want me to do about mod 19? So like if I take 7 squared in mod 19, that's not anything real close, right? 49 doesn't jive very well with 19. It's not going to give you a simpler number. So what do you suggest I do with this one? Fermat's little theorem. Yes, I would definitely take this as a prime modulus with no power on it. So I can use Fermat's little theorem, which would tell me that 18 powers of 7 could be canceled to 1. So what you need to do here, guys, is you need to go off on a little bit of a scratch paper and you need to divide 2006 into 18. Because you need to know like how many factors of 7 are going to be left over after you put these sevens into packs of 18. So there's going to be 1 here. Subtract 20 minus 18, we get 2. Put another 1. And then subtract again, we get 26. Put another 1. And subtract again, we get a remainder of 8. Okay, so something like that is a scratch work calculation that I would totally feel no guilt asking you to do on the test. So you should be able to do something like that. But the point is that this is 7 to the 18 to the 111th power times 7 to the 8th. Right. And the first part by Fermat's little theorem, and you should cite that, guys, Fermat's little theorem. You can just write FLT next to that, and that's enough for me to know that you are aware of what you are using right here. It just becomes 7 to the 8th. Well, 7 to the 8th, this is going to take just a little miniature calculation. I'm going to write it as 49 to the 4th. So 7 squared would have been 49, and I raise that to the 4th. But 49 in the world of mod 19, I am going to reduce it down to, let's see, -8 would be fine, or +9, either one. So I'll use -8 to the 4th. So you just have to brute force this part, guys. This one is not going to come quickly. Just have to suffer through, right? 8 squared is really 64 squared. And again, I'm going to reduce 64 in mod 19. In mod 19, 64 should reduce to 7 squared, which is 49, which again reduces to -8. So that was not the slickest simplification possible, but you know, in the real world, this is what could happen. Right? The theorems do not really give you any shortcuts. Okay, but what I want to do next, guys, is I want to show you how to write up the rest of this solution. You should really try to follow this template. I think people, hopefully on the homework that you just turned in, were able to follow this same template, but I want to show it to you once tonight. It is very, very likely that this will be on the test because this is such a commonly used thing. Namely, what we're saying here, guys, is that 7 to the 2006 satisfies x congruent to 1 mod 8, x congruent to -1 mod 25, and x congruent to -8 mod 19. So we have basically proven that so far. Through all of that blue writing in the middle board, we have kind of verified that 7 to the 2006 satisfies all of those things. What you need to do now is actually figure out how to solve this system that I just put a box around as a standalone system of equations. Yeah. As a standalone system of equations. And how would you do it? Yeah, it's a system of congruences, guys. If it's a system of congruences, I'm probably thinking CRT. And the mods are pairwise relatively prime. So I can use that. So we use the CRT. Again, you should write that on your paper so that I can give you points for knowing that this is what you're supposed to use. We're going to use the CRT. And here's where you need to remember how the solution goes. So the X solution, if you remember, there's this notation, which I'm going to review in just a second. A1, N1, Y1 plus A2, N2, Y2 plus A3, N3, Y3. So we actually can construct the solution as part of the proof. Well, this is part of the proof of the Chinese remainder theorem that you're probably learning as one of the theorems for the exam. At this point, you just need to figure out, well, what are what are all of the numbers that you need to calculate in this formula. So the A values are just the 1, the -1, and the 8, or -8, right? And then the big N's, remember that N1 is the product of the other two mods. So it's going to be 25 times 19, which I believe is 425. No, 475. And how am I multiplying these together in my head? This is just real world common sense. I'm taking 25 times 20. 25 times 20 would be 500. But that's one too many factors of 25. So I have to take 25 away from 500, leaves me with 475. Okay. The N2, that's going to be 19 times 8, right? So again, if it was 8 times 20, it would have been 160. But I only have 19 factors of 8, so I have to subtract one factor of 8 from that, and it's 152. Okay? And last but not least, N3 is 25 times 8. That one's pretty easy. That's just 200. Okay? Everybody comfortable with that? How I'm getting those big N's? So big N1 is the product of the second and third mod. Big N2 is the product of the first and third mod. And big N3 is the product of the first two mods. That's how you calculate that. And I did them in my head, but of course, feel free to scribble down a little calculation if you need to. Okay, so now I would like to find the Y values. This is the hardest part. For the N1, we now take 475 times Y1, and we set that congruent to 1 in mod 8. Okay, in mod 8, we have to do that. And the good news here is that the mod is not very big. I just need to reduce 475 in mod 8. And yeah, because 400 is already like 0. And so you're like starting over with 75. In mod 8, 75 is the same as 3. So this is really 3 here. So it's like 3 times what gives you 1. And if you do that in your head in mod 8, I'm totally okay with that. You don't need to show me you can do linear congruences here. You can just eyeball this. If it's a small enough mod, Y1 is going to be 3. And that's in mod 8. Okay, so we get Y1 to be 3. Now let's go on to the next one. We have 152 times Y2. This is supposed to be congruent to 1 in mod 25. And in mod 25, 150 would be 0. So it's really just 2y2 equal to 1. Can somebody eyeball it and tell me what y2 could be?
Should it be congruent to negative?
13.
It would be 13. Did I mess up? Oh, no, it should be a positive one. These a values don't come into it. So when you're solving for the y values, you always have 1s on the right side. Yeah. And so, yes, what Kim noticed is that if I take 2 times 13, right, so 13, then in mod 25, 2 times 13 cancels out to 1 again. Right, so it's just 26. 2 times 13 is 26, but that's the same as 1. Okay, so that's the y2 value. So far, so good? Okay. Finally, the last one is 200 times y3 congruent to 1. And this one now we're looking in mod 19. Now, guys, in mod 19, I'm going to do this mostly in my head as best as I can. 190 would be the same as 0 in mod 19. So I can wipe away 190, which only leaves me with 10 here, right? And now I'm just looking, can I solve for y3 in my head? Can I come up with a value for y3 so that 10 times that becomes 1 in mod 19? Anybody think they can just eyeball it?
2.
2. Yeah, these are really easy. 10 times 2 is 1 in mod 19. So that's just 2 in mod 19. Guys, do you have to eyeball these? No, you can just use your Euclidean algorithm, divide 19 into 10, and that goes with a quotient of 1 and a remainder of 9, and then just do, your whole Euclidean algorithm forward and backwards. So there's always a backup way to get these solutions. But if the mods are small and the numbers are small, you probably can do them in your head. Okay, so then my answer for x would be 1 times n1, which was 475, times y1, which was 3, and then plus -1 times n2 is 152, times y2, which is 13, and then plus A3, which we said was 8, times N3, which is 200, times 2.
Professor, isn't A3 -8?
A3 is -8. Yes, I keep forgetting my minus sign. Thank you. -8 right here. Awesome. And I have to be honest with you on this. This is just a pain numerically to calculate it out. I mean, without a calculator, this is going to be a little bit brutal. But when I write my review session questions, I don't care quite so much if it's going to be brutal for anybody, it's going to be for me. So I worked it out, but I don't know if I got the exact same thing in the right modulus here. So I am going to suffer through with a calculation. I think, oops, no. 1425, that's the first one. And then, oh, this one's bad. 152 times 13. I'm just gonna, I really do want to get the right answer here. So that's -1976. And then minus the last one is, well, 16 times 200 would be 3,200 with a minus on it. It's looking like that. And so if I clean this up, I'm going to get an answer that's not going to work because this is going to be negative. Let's take 1976 and 3,200 and combine it. Is 5176. If you guys don't want to take massive notes on this and just kind of follow along, it's totally fine with me. Now I'm going to subtract them. 1 and a 5 and a 7 and a 3. Negative 3751. So that is not going to be a remainder. Like when it says find the remainder when you divide this number by 3,800, you should not be expecting a negative answer. So what are you going to need to do with this answer here? Add 3,800 to it to make it positive. When you add 3,800 to negative 3751, you get 49. And this is mod 3,800. Remember, the CRT gives you a solution in the mod of the product of these. Okay. So am I done now? The way you can really make it tight, the way you can really clearly wrap this up is you can say that note that 49, which is the number we just came up with, is also a solution to this system. This system being that system. So 49 solves it. We just worked all that out. But 7 to the 2006 also solves it by the work we did over here. And because of the uniqueness part of the Chinese remainder theorem, I want you guys to almost just memorize this sentence because if you just rubber stamp this down, it's going to be really good. So by the uniqueness part of the CRT, by the uniqueness part of the CRT, 7 to the 2006 is the same as 49, and this is in mod 3800. It is congruent to 49 in mod 3800. That's right. So that took a bit of work, but it covers a lot of ground, right? We used Fermat's little theorem. We used the Chinese remainder theorem. We put them together. This is so important because cryptography is all based on doing that exact same thing, which we're going to talk about next week. So I definitely want people to understand and appreciate both of the theorems individually, right? The Chinese remainder theorem and Fermat's little theorem individually are very important, but seeing how they work together is even, I think, a more impressive way to use these results. I would definitely be expecting this kind of problem. Maybe the computation is not quite so bad, but who knows? But the point being, this style of question that uses this material would be good. Again, if you made a little goof, one of these numbers, like I miscopied this as an 8 instead of a -8. If something like that happens, it's not going to ruin your exam, right? Because I'm going to see that, oh, they know exactly what they're doing. They just miscopied a number. It's not a big deal. But try to get the method down for how this works. Okay. Questions here? Can I do just one more last problem? This one will be faster. That way I will actually feel like I've pretty much done my whole sheet. And that way you guys, if you want to come tomorrow, it's fine, but you won't see anything new probably. So it would only be if you just want to kind of review the ones you've already seen. Because I'm really getting down to my last examples here, and I feel like almost everything is being covered, but there was one more problem that I thought would be good to show you guys. And this one will not take us long. It's a proof, it's an abstract proof, and it's involving something very basic. So we don't have to bend our minds too much on this, I don't think, but I just want to show you this one last problem. Number 9. The catch is I'm probably going to be late to my office hours, but that's okay. I'll be back by probably 8:30 instead of 8. It's not a big deal. So here it is. Let's let A, B, and C be in the positive integers. I would like to prove that the GCD of the GCD of A and B with C is equal to the GCD of A with the GCD of B and C. I have to read that very carefully with the right spacing between words so that it makes sense. Guys, we never really talked about, like when you define the GCD function, it's only for 2 integers. Like there is no definition of what's the GCD of ABC. There is no definition of that. And it would depend on, well, are you doing them like 2 at a time, or are you taking all 3 at once? And it's not a well-defined expression. Like this is not a notation that we have. Like the GCD is a function of 2 inputs. So what if we had 3 numbers here, right? I can't take a 3-way GCD. So this setup arranges so you are never looking at more than 2 numbers at one moment to take the GCD of. Okay. Whenever, I think there's been a couple homework problems like this. This has not been a really strong topic that we've used a ton, but it is something that you've seen. If you want to show that 2 different GCDs are equal. So the greatest common divisor here is equal to the greatest common divisor here. What you want to do is show that all of the common divisors on this side are the same as all of the common divisors on this side, so that you can then just declare that the greatest one here is the same as the greatest one there. Right? So what I would probably do here, guys, is I would probably, for the solution, I like to do this in sets. I like to set S to be the set of common divisors of the GCD of A and B and C. Okay. So S is the set of things that are common divisors of these two numbers. This is a number, this is a number. By the way, you could relabel this as D if you wanted to. It's only going to add more alphabet soup of letters to what you have. I don't recommend it. It's not really conceptually helping the proof that much. So you can relabel if you want, but I honestly think you just write it like that. It's no problem. And I'm going to make another set almost the same exact way. The set T is the common divisors of A and the GCD of B and C. So I go with the left side for S, the right side for T, and the claim is that S is equal to T. Keeping in mind that S is not a number, T is not a number. These are sets. And I'm going to prove that these two sets are equal. If I'm successful in proving that claim, then I am done with my proof. Because if S is equal to T, we can say from this, the result is immediate. Or in other words, it's clear, if I could use that word around here. It's clear because the greatest, now if two sets are equal, and this is just a set of numbers, this is just a set of numbers. So the biggest thing in this set has to agree with the biggest thing in this set if they're equal. Okay, so I don't really need to prove anything more beyond just this right here now. So I like setting it up like this. Now, because these are sets, the way you're going to want to prove this claim is that each one is a subset of the other, right? So let's start with showing that S is a subset of T. And for that, I'm going to, let X be an element of S. You can use whatever letter you want. And I'm going to try to show that X also lives in T. Now, the fact that X lives in S means what? It means it's a common divisor of the GCD of A and B as well as C. So then X divides the GCD of A and B, and X divides C. So pretty much just not doing any real heavy thinking here. I'm just kind of writing down what things mean, right? So X lives in S, then it divides that guy and it divides this guy. But guys, the GCD of A and B is a divisor of A and of B. And so if X divides, so remember, do you guys remember divisibility is transitive? If one thing divides another and then another divides another, then the first one divides the third one, right? So that actually means that X divides A, X divides B, and X divides C. So it divides all three of them. And now, by problem number 2 from this review session, I probably should have done this one earlier. By number 2 from the problems we did earlier today, we said that if there's a common divisor of two things, then that is also a divisor of the GCD of the two things. So I'm going to put these two together because I see that for T, I want to put the B and the C together. So by number 2 from today, X divides the GCD of B and C. Yeah. Well, but X was already a divisor of A, and now it's also a divisor of GCD of B and C. So it's a common divisor of A and GCD of B and C. Now that means that X lives in T. So X lives in T. Everybody with me on this? A little bit abstract, but I hope it's reasonable. Yeah, so we get, sorry, just checking my phone here. We get that S is a subset of T. And then I'm just going to say, and this is another one of these things, guys, where it is completely similar. Similarly, T is a subset of S. You would not be expected to like write that part all out because it's just changing the order of the letters and more or less the same reasoning again. And you can save yourself 3 or 4 minutes by just writing that down. If you have a doubt during the exam about whether I would object to you just saying it was similar or not, you can come up and ask me and I'll do my best to give a neutral answer to give an answer without spilling the beans about the question. I'll try to help you with that. Okay, but that now shows that, so then once you know both of those is true, then S is equal to T, which is the main thing that you had to show here. Okay, so if anything I've done tonight has kind of jiggled your mind a little bit, like, oh, maybe I need to review another example of this, you'll find back in the homework that we did some of that. And then, oh, what about the Chinese remainder theorem and Fermat's little theorem put together? I think that between these 9 problems, I've covered a lot of the ground. Like, I'm trying to think, is there any gaps of what we learned that I haven't talked much about? I mean, I did Diophantine equations. I did CRT. I did the variation of the CRT. Right? We did linear congruences, induction, modular arithmetic. I feel pretty good, like for these first 6 weeks of the semester, that most of the concepts were either mentioned or used in some aspect of what we did here today. What do you guys think? Are there questions? Brian?
Maybe in the next review session, if you get to it, maybe a question on like quadratic congruences.
The quadratic congruences, yes, we didn't do much with those. It was really just, and that is something you should review. It's on the review sheet, and you're right. So that would be a gap. But it was really just, okay, so when does the congruence x squared plus 1 congruent to 0 mod p have a solution? And it was literally just if p was of the form 4k plus 1. If it was of the form 4k plus 3, the answer was no. So that's in theorem 5.5, I think it was, if I remember correctly. And the only thing I could ask you with that would be like, could you actually come up with a solution? In the proof of theorem 5.5, the solution is actually constructed. I think it's p minus 1 over 2 factorial. So you just have to sort of crunch that calculation out. And then whatever solution you get, the negative of it is also a solution, right? Because when you square the x, the minus sign becomes irrelevant. So yeah, I'll see if I can come up with something, but it's probably going to take 2 minutes. It won't be anything too substantial. Other questions? Well, I stole an extra half hour for you guys. I appreciate it. But like I said, this is short by my standards from the old days. But I think I feel pretty good. I think I feel pretty good that we got a lot of good stuff done here. So I think I'll call that good. I am going to go take a break, probably until at least 8:30. It might be more like 8:45. I'll be coming back. I'll be in the office all evening if anybody wants to ask me more questions about anything. Otherwise, go home, get some rest, and get a fresh start tomorrow. I'll be back tomorrow as well. not only for the review session, but also more office hours. Yeah.
Do you still feel like if we came today, we don't need to come again?
I don't think so. I don't really think you would need to come tomorrow. I mean, I will record tomorrow's and I'll send it out. And if I realize tomorrow night that, oh, I actually did 2 or 3 things that the first group didn't see, I might, in my email, I might say, oh, by the way, this review has such and such that wasn't in the first review, just to give you a heads up to look at it. I wouldn't, unless you want to come down to sit through it again, just to absorb it, I wouldn't come down just for the sake of like hearing something new. Because that's 2 hours you could probably spend doing something else. But because you never know, somebody could ask me a question tomorrow night. It's like, oh, well, gee, we should like talk about that. And then I might realize, oh, well, I didn't get to that in the other review. So I'll try my best to be clear about that in my email. Yeah. Okay, great. And everybody out there in Zoom land, I am going to turn this session off and go take a little break. Okay, thanks for coming. Bobby, Edgar, Kiana, Kim, glad you guys could make it.
Thank you, Dr. Hammer.
You're welcome. Have a good night.
You
Bye,
too.
everyone. You're welcome. Bye-bye.